Welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Aribut College, University of Delhi. So our today's topic is about virtual memory and demand paging. As you all are aware that presently we are going through the operating system series, and the previous topic which we covered was about memory management techniques. Now the idea here is, why do we want to have various techniques to manage the memory? The bottom line agenda behind that was, we want to keep many processes, multiple processes in the memory, because we want our system to be a multi-programming system, and we want these processes in the memory simultaneously to allow multi-programming concept. Now coming to our today's topic, which is very we can say related to these memory management techniques, is about the virtual memory. Now let us first try to understand what is virtual memory, and then we will establish the connection between the previous topic and this, and we will be able to connect the dots. So virtual memory is basically a technique that allows the execution of processes that are not completely in memory. So you all are aware that whatever processes, data, functions, everything which a CPU wants to execute has to be there inside the memory. Now here what are we saying is just we can say opposite. That means, I repeat what I said, is virtual memory is a technique that allows the execution of processes that are not completely in memory. Now when I am saying not completely in memory, that means I am saying that some part is already in the memory and some part can be taken in the memory on the basis on as and when basis, when it is required. Now what is the advantage behind this idea of having the virtual memory, which allows to keep the processes other than to keep the processes in at some storage which is other than main memory? The advantage here is the program can be larger than the physical memory. So for example, your total physical memory which is available for processes or for programs is, let's say, X units, and your program is the total size of the program is Y unit, while your Y is greater than X, then also it is possible to execute that program with the help of virtual memory, because your virtual memory actually abstracts the main memory into an extremely large uniform array of storage. That means it actually virtual memory is an abstraction of the main memory. Now what kind of structure this main memory or this abstraction of main memory is having is the large uniform array of storage bytes or storage words, we can say. Now what are we doing here? We are actually as we did in our previous memory management techniques of segmentation and paging, we are separating logical memory as viewed by the user from the physical memory. Now all these memory management techniques are, we can say, actually a win-win situation for both the sides, for hardware, for processes, and for the programmers or the users also. So how come? Let us try to understand this. Basically, when we are saying that separating logical memory as viewed by the user from physical memory, this is what the one of the advantages of virtual memory technique is, because it is what it is going to do, it frees the programmer from the concern of memory storage limitations. Now programmer can freely execute a process which is of Y size, or Y having the size of Y units, where these Y units are more than the total size of the memory. So now programmer is not at all worried about the memory storage limitations. Also, as far as this other side of the coin, when we see the processes, these processes are allowed to share file easily, and implementation of shared memory, which we have seen in our initial lectures, has been it's now very easier. Although there are some implementation challenges while implementing the virtual memory technique, but these are these challenges, we can say, are manageable, or we can handle them with care. But yes, we have to be very, very cautious here, because this may substantially decrease the performance if your virtual memory is going to be used carelessly. How, that we will be taking in our upcoming lectures, that how it may substantially decrease the performance as well if it is used carelessly. So, the caution here is that virtual memory technique is actually a win-win situation for the programmer as well as for the processes, but this is to be used very, very carefully. Now, see, what is what is a general scenario when a program is being executed? Do you really think that entire program at once is needed? Actually, that is not the situation. Entire program is not needed at once. For example, a program is having let's say we can say, for example, 10 options in a particular menu. Now, all these 10 options in a particular menu are not required at a single point of time. These are required as and when the user is looking for those choices or typing the concerned button, we can say, or something of that sort. So, the entire program is not needed at a particular point of time, and these programs often have code to handle the unusual error conditions. Now, these unusual error conditions, although this is a clean programming practice to have the we can say error handling code within the program, but these codes which are there to handle unusual error conditions are seldomly required. I mean, they are not required very often. Apart from that, for example, we have an kind of, let's say, array, and someone has declared an array of, let's say, 100 elements, but actually it is a common practice that out of those 100 only maybe, let's say, 30, 40, 50 are being used, and the other 50 are kind of, we can say, are kept aside uselessly. So, this can happen with arrays, lists or tables, which often allocate more memory than they actually need. So, that is also one of the kind of situations. Then another situation is, let us assume the example of a assembler symbol table. So, this assembler symbol table may have some room for 3000 symbols, but the average program is having less than 200 symbols. So, what is actually being happening here is the what point I am trying to establish here is, first, entire program is not needed at a point, and all the codes or all the data which is clubbed or which is there with the program is hardly used at a time, and it is often an exaggeration of the storage space. Now, we can also say that virtual memory, by using virtual memory, we can execute a program that is not fully in the memory, or we can say the virtual memory is the ability to execute a program that is only available only partially in the memory. There are no constraints of physical memory limits for the program, as I have already told you that the program can be bigger than the total size of the physical memory. Then also it is possible to execute it. And here, by using the technique of virtual memory, users would be able to write programs for an extremely large virtual address space. So, because that address space which we are going to opt as the virtual memory is going to be very, very large. So, users are able to write programs which can use extremely large virtual address spaces. Now, because each user program could take less physical memory, more programs could be run at the same time. So, for example, I am having a physical memory of, let's say, size y, where I am having 3 programs of size x1, x2, x3, which is obviously in total going to be more than y, but I can keep all these programs x1, x2, x3 in memory, because at a time I do not need all the whole programs. some part of x1 can be there, another part of x2 can be there, third part of x3 can be there. So basically your each user program is going to take less physical memory, and it's most of this part is stored at some other we can say storage space or some other storage device. More programs could be run at the same time, and this is what how your virtual memory is allowing the technique of multi-programming to happen here. Now what is happening if we are having more programs, more processes to be run at the same time, and all these are available in memory? This ultimately results in CPU utilization and throughput, but one point which is worth noting down here is there is not going to be any improvement in response time or turnaround time. Response time and turnaround time of jobs are going to be the similar, but yes, CPU utilization and throughput are basically going to be, or definitely going to be increased. Also, less input output would be needed, so that each program is going to run more faster. Now what is happening in this technique of virtual memories, some part of a program or a process is stored onto the physical memory, and some part is stored on a backing store, maybe your hard disk or some other storage device, and as and when required, that particular part which is stored on the hard disk is being we can say swapped in inside your physical memory. So virtual memory basically involves the separation of logical memory, which is as it is perceived by the user, from physical memory, and this separation allows an extremely large virtual memory. Now why we are saying virtual memory? Because that's not the physical memory, that is something which is existing in virtual, because that's maybe a part of hard disk is being used as virtual memory space. So the memory space is being called as virtual. This separation of virtual memory from physical memory is going to allow an extremely large virtual memory space to be provided to the programmers or for the programmers when only a smaller physical memory is available. So as I told you, the physical memory which is available is smaller, but the virtual memory which is being provided is kind of very large. Now here we have virtual address space and physical address space. So the virtual address space of a process refers to the logical view or the logical address space, or we can say it refers to the logical view of how a process is stored in memory. Now it is up to memory management unit, which is MMU, to map these logical pages to physical page frames inside the memory. Now what is happening here is virtual memory allows files and memory to be shared by two or more processes through page sharing. So there are pages which are being swapped in and swapped out of memory. So these pages are allowed to be shared. So virtual memory here is allowing files and memory to be shared by two or more processes, and the idea here is about page sharing, and I am sure that with previous lectures you all understand what is the page and what I am talking about. Also, not only the memory and the files, but system libraries can also be shared by several processes through mapping of the shared object into a virtual address space. That means the object which is going to be shared, or the library or the file which is going to be shared, that has to be mapped into virtual address space, and because of that mapping of shared object into virtual address space, it can be used it can be shared by several other processes. And also I have already told you that processes can also share memory, of course. Now virtual memory allows one process to create a region of memory that it can share with another processes, and processes sharing this region consider it part of their virtual address space. Yes, yet the actual physical pages of memory are shared. So this is what the we can say totally features of the virtual memory, or why it is happening, how it is happening. So basically just to kind of we can say recall in a nutshell, we can say virtual memory technique is one of the technique which allows the processes to store a part of it inside the physical memory, and other part which is not currently required inside any backing store, for example hard disk, and as and when that particular part which is residing on the hard disk is required, can be swapped in, can be taken in inside the memory. But this is, we can say, a kind of a macro level view of what actually virtual memory is. So virtual memory is using a part of hard disk or any other backing storage as we can say as physical memory, but yes, not we can say in a physical manner, but in a virtual manner. So that is what your virtual memory is. The process is not completely residing inside the physical memory. Now the concept which is very kind of close or come under the implementation details of virtual memory technique is demand paging. Demand paging, as the name suggests, these pages are loaded as and when they demand it. So basically demand paging technique says that you are supposed to load, or a process is supposed to load the pages or the data only as and when they are needed. So for example, I am having a although I am taking a smaller example here, but this is the example which you all must be familiar with. So it will be easier to comprehend. Now let's say I am having a linked list, a program of a linked list, and it is having, let's say kind of, let's say 10 options. 10 options as in first of all the creation of the linked list right from the scratch. Then you have insertion into the linked list, then you have insertion at head into the linked list, then you have insertion at tail into the linked list, then some good 3 versions of deletion, then there is searching, then there is reversal of a linked list, and so on and so forth. So all these are modules or available options from which the user is going to select. Now your program starts with a list of these available options, and user is told to select the option which what kind of action he or she wants to perform on that particular linked list. Now what is happening? At a particular point of time, user is going to press only one choice, or user is going to enter only one choice, and corresponding to that particular choice the module is required. So the idea is we don't need all the modules at one point of time. So the bottom line is we need to load the pages as and when they are needed, as and when they are demanded. So here is the technique of demand paging, which is very commonly used in any of the virtual memory systems or virtual memory technique implementation. So with demand paging, virtual memory pages are loaded only when they are demanded during the program execution, and if there are some pages that are never accessed, will never be loaded into the physical memory. Now what can be we can say what can be the example of these kind of pages which are never accessed. So for example, I am having a particular code which is kind of related to try and catch, let's say in C++ or maybe in Java or Python. So that is related to an exception handling. So when is an exception handling code is required? Only when an exception is kind of raised or an exception is thrown. So there is a possibility if a program is going in a clean and clear, crystal clear manner, it may not require this exception handling code whole throughout its execution. So the pages which are never accessed are never loaded into the physical memory. Now demand paging, if you can see very closely, is similar to the paging system with the facility of swapping, where a process resides inside the disk memory. Now what is the we can say difference between the demand paging system and the paging and we can say the normal paging technique which is implemented with the help of swapping is rather than swapping the entire process into the memory, only those pages which are required will be kind of swapped inside the memory, and this task is done with the help of a lazy swapper. Lazy swapper is not going to swap any page into the memory unless it is needed. Now, when I am saying that this is the difference between demand paging and the normal paging system with swapping, the use of the term swapper is, I can say, is technically incorrect. So, the better idea is to use the term pager rather than swapper in connection with demand paging. So, whenever we are kind of talking about demand paging, we will be using the term pager, and whenever we are talking about the normal paging technique along with the swapping, it is okay to use swapper. So, in the context of demand paging system, the use of swapper is technically incorrect. Swapper, because the swapper is going to change, swapper is going to take, or swapper is going to manipulate the entire process, while the pager is concerned with the individual pages of a process. Now, in order to understand this whole concept, let us take a look at the figure which is given on the screen. Now, let us say in the main memory there are two programs. One is the program A. There are two processes, program A and program B. Now, let us say there are let us say our physical memory is limited. Presently, program A is occupying some of the space and some pages of program A are already in the memory. Then program B also wants to get themselves executed, and we want some space for that. So, what is happening here? Some pages of program A, for example, the page number 4, 5, 6, 7 are being swapped out. Swapped out, that means they are being now stored on the hard disk, while in the space which is being kind of we can say being which is kept vacant by program A will be utilized by program B, because the page number 17, 18 and 19 are being swapped in from your hard disk inside the main memory. So, the process or the pages more technically we can say, because we are talking about demand paging. So, the pages of a particular program or process when they go from, or when they are swapped from main memory to the hard disk or any backing storage, this is the process of swapping out, and whatever pages are required, those pages are being swapped in the main memory from the your hard disk or the backing storage. So, this is what the kind of we can say process of demand paging in a nutshell. Now, demand paging, as the name suggests, there is a particular kind of meaning, or there is a specific meaning of this particular term which is demand. That means as and when the demand comes, then only the pages are going to be we can say swapped inside the memory. They will not be swapped in unless the demand comes up. So, without demand they will not be taken up. Now, the point is, how are we going to kind of we can say distinguish between what are the pages available in the memory and what are the pages which are available on the disk. So, here we need the support of some kind of hardware which is going to make a system distinguish between the pages which are available in the memory, or we can say the pages which are not available in the memory and all stored on the disk. So, there is some kind of hardware support which is required here. What now, this hardware support in detail we will be covering in the next lecture. Let us take a recap what we have kind of gone through in this lecture. We have started with the technique of virtual memory. Then what are the characteristics of virtual memory that we have seen, why it is needed, why it is a kind of beneficial situation for both user as well as for the processes, and so on and so forth. And then we have seen demand paging technique, how it is being what actually demand paging is, and how these pages are being distinguished, whether available in the memory or available in the disk. That we will be taking up in our upcoming lectures. Hope you have enjoyed the lecture. Here is a reference which is of the book Operating System Concepts by Silberstadt and Galvin. This is being used as a reference for preparation of this lecture. Hope you have enjoyed. I will see you in the next lecture. Till then, take care. Goodbye.